here I am. Good morning, everybody. Just starting up in a second. I can see that there's a small but committed audience on YouTube and on Twitch. Probably a few folks on streams. So now I can make myself small. Good morning, folks. Great to have you joining me. For those coming in live, great to have you here this morning. Week 7, Lecture 2, Thursday morning here in Canberra. For those watching later, thanks for joining me as well. As you all know, we've got the team available now, so if you've got a question or any thought or anything at all you want to shout out on the team, just chuck in a comment, let me know you're there, and we can get started pretty soon. This is the second half of our lecture this week on data structures. Data structures, which is really about developing with assembly programming in this sort of very primitive and simplistic form, the bare bones DIY approach to creating things that you've used every day in your high level programming experiences. Things like arrays, which we worked on Monday, or Tuesday actually, sorry. Arrays on Tuesday. And we're working today on a data structure which is often called a struct, but we're calling it a record today. So these are two really important core data structures. Very much a part of everyday experience with high-level programming, things you'd learn in about week 2. But in assembly, it's taken us a little while to get here because we've had to learn a few different kinds of things to really have the tools available to us to get into these topics in detail. So I'll skip to records in a minute, but just going back to the admin time slide, the probably very important piece of admin information for you would be that the mid-semester exam is tomorrow, so don't forget to do it. We've got I'll go to the page about it. COMP2300, COMP2300, it's me. Mid-semester exam, 22 April 2022. I'm going to send everyone an email with this information so there won't be any missing pieces. That it will start 16:30 Canberra time. It will go for 90 minutes. It's worth 20%. It is happening on Wattle. There is a link somewhere. I will put a Wattle link on this page so it's very clear. It's an open book exam. All materials are allowed, but of course it's an individual task. You're absolutely not allowed to collaborate. I just want to point out that I'll publish some information today to help you record your screen during the exam. This is something which we ask everyone to do, both as a kind of absolute gold standard record of what happened in your exam. So if there's any need to prove that you wrote what you did in your exam, you've got a video there with that information. We've also got this important other aspect of it, which is that if for some reason you lose your internet connection or something technical goes wrong with Wattle, you can then use the screen recording to back up the information in your web browser, which you might otherwise not have been able to view. So this is something which we do in this course. I know other courses have different approaches, but you'll have to practice this today or tomorrow morning, I would suggest, so that you are able to make a screen recording. The best way to do this is to have a webcam just showing your face and your screen there. in most situations, the vast majority of situations, you will never have to show anyone else this recording. But if you find that you've lost your exam somehow or Wattle has gone wrong, then you can send us this video and say, look, here it is. This is what I was doing in my exam. And that will be a great standard of proof to help us to make sure that you did what you say you did. So that's info about the mid-semester exam. If there's any questions about it, you can ask on the team right now, or you can ask them on Piazza. So we were talking about data structures on Tuesday. We've done arrays, but just going back to the basics here, different kinds of data require different kinds of structures to really give us the most convenient way as programmers to access them. So the handy thing with an array is if you had a whole sequence of data which is the same, then you can put it in little equally sized chunks of memory, and then you can iterate over those equally sized chunks with a loop. And that's what we did on Tuesday, different types of arrays. The other type of data structure we're going to talk about today is the different problem where you've got a bunch of data which is different, but it's related. So you've got one kind of thing and you maybe have a number of different descriptions of it. Like a student has a number of classes, a student has a phone number, a student has an email address, a student has a mark for COMP2300 assignment 1. You can have all of these data associated with a record. It's similar to what you might have experienced in your Comp2300 class on Java, where you're using objects which have these fields for different kinds of data. These aren't object-oriented objects, but it's a similar kind of idea of associating a number of different kinds of data together. So I'll go back to my record link. We're going to skip all the way to that part of the lecture. Here we are, records. We made it. And start to talk about it. Records, as I said, they're for collections of heterogeneous data. Heterogeneous means different kinds of data. And Wikipedia says a record is a collection of fields, possibly of different data types, typically in a fixed number and sequence. The fields of a record may also be called members or elements, although these risk confusion with the elements of a collection. Okay, so when it starts talking about collections there, that's a bit off topic, but let's focus on the first bit. A record is a collection of fields, and each field is possibly a different data type. Typically, you've got a fixed number of these things, and they're in a fixed order. So the record has each item of these, each of these fields, each of these pieces of data in a fixed order, which is important when we're thinking about how these things are placed into memory. Yes, records might also be called structs, tuples, objects, although these terms can also mean different things. There's a lot of history of people designing different kinds of programming environments, having different ideas about data structures, and renaming similar ideas to mean their kind of thing, right? The kind of thing for my programming language is going to be called a tuple, or it's going to be called a, field collection X or something, right? We just make up things just to make them so they make sense to us, make sense in the programming languages that different people have designed over the years. The context matters here. In the context of COMP2300, in a bare metal assembly, we're going to call these things records. Just to hit the metaphor one more time, you could think of this as being an array. A bunch of things that are all the same, that get stacked up, and you can see them, you can iterate over them through memory. This one might be address 0, address 1, 2, okay, where's my green pen? I'd love a green pen. 0, 1, 2, 3, 4, etc. Oops. A record is going to be a big stack of stuff. A big stack of boxes, all in a cupboard, and we know where everything is, but don't try to iterate over it neatly. It doesn't work like that. Probably don't take the metaphor too far here, but this is what you might think of a difference between an array and a record. Let's think of some simple examples, and we're going to start doing worked examples in a minute. Imagine that we're making a character for a computer game. It might be a kind of collectible monster game, or it might be a game of where multiple characters are competing for fixed resources in time while expanding their character over a period of time. In this instance, we might have a name for each character. We might have a kind of record of the life force of each character, its health points, HP. We might have a record of its magic power or mana. And just as we were saying before, these might be different kinds of data because both HP and mana are a word, so they're going to be some kind of number. I guess I'll say that they're unsigned ints. And the name is going to be 16-byte null terminated ASCII array, or we'll say it's a byte array, but it's that data structure, a byte array, is defining a string, an ASCII string. So different kinds of data can be combined into a record. Another example, a synthesizer for making music. You might have different musical parameters, frequency, phase, amplitude, type of waveform, and all of these things could be a number. Some of them might require a whole word, but we might want to save some memory and make one a half word, so the type of sequencer will only be 16 bits, not 32 bits. So two examples of different kinds of data that could be used in a record. Here's an example of how these could work in memory. Here's the character example. It's going to be, we've got one word here for the HP, and that's going to contain the number 62. One word here for mana, that's going to contain 155. And then a string for the name. Each byte contains a different letter, and the string is Zoltan 00000. So the name of the character is Zoltan, and then we've got just a bunch of zeros padding out the rest of that that array. Yeah, so it's got to be 16 bytes for the names here. You can see how this is structured in memory. We've got starting, for instance, at memory address 0x2008. That's the first word, HP, then C for the second word, and 16 for the name. Similar idea for the synthesizer data, a word, a word, a word, and then a half word, 2 bytes for the type. And those are the addresses going up, incrementing by 4. 0104, 0108, 0112, 0110, 0116. So one thing to point out here, we said before that a record is usually a fixed size. So even though we're only using 1, 2, 3, 4, 5, 6 letters for the name of our character, our record defines this field, the name field, as being 16 bytes in length. So we have to have it 16 bytes in length. It wouldn't be a record, or it wouldn't work in this definition of a record if we just cut down that string to be 7 with a null termination. That would be a different kind of thing. What's the difference here? Two different, I suppose, kinds of records for the same thing, both the synthesizer record. This one is frequency, phase, amplitude, and type. This one over here on the right is frequency, type, phase, and amplitude. What is the difference? In this one, the type comes last, and this one, the type is second. What difference does that make? Well, it doesn't make a difference in terms of how big our record is. It doesn't make a difference in terms of what data we're storing. It does make a difference in terms of where the data is within the structure. So the point of a record is to have a regular structure for things that combine these kinds of data together. So in this one, you could say that the phase or the frequency is at the base address. Phase is at offset +4, one word. Amplitude is at offset +8, two words. And type is at offset +12, three words. Over here, phase is at offset +10, +6, sorry. And amplitude is at offset +10. So we've got a problem with these two records. If we were recording two synthesizers and we had different field orderings between our records, the offsets would be wrong when if we were trying to access the data from the second synthesizer. So records have, our definition of records in this lecture is that they will have a fixed order of fields, which means that once you've got a specific kind of record, all records like that have the same offsets within them for accessing the different fields, which will be useful, as I'll show you in a minute, when we're actually trying to code with these things. So here's the hack of a record. Once you know the structure of your record, if you want to access the data within any record, you only need one extra piece of information, which is the starting element of that record, because you can do all of your other memory accesses and stores using offsets from that base address. Whew. So this is why there's efficiency in defining these data structures regularly. So we have a fixed definition for a record. We decide for our synthesizer record what the orders of the fields are and what size those fields are going to be. We make that design decision. Then we've got our fixed design for that data structure, and we can use it multiple times within a program and gain some efficiency by not having to cart around all of the metadata for each different data type and have everything as separate independent variables all over memory. We can just remember one memory location and the schema for how our data structures should be designed. Okay, let's do a record. Records by request. Time to get started with the coding. Hope I can remember how to do it. Let's do the Zoltan one. I'll just go back and remember what the record was supposed to look like. I've still got my array sum from last time. I might get rid of that so I don't have a bunch of stuff all over memory. I want to put I guess it doesn't matter where I put it, but I will put it right here before my array that I was playing with last week. And it's going to be called Zoltan. Whoop, stats, that's the label for my record. And we're going to start with a word, which is going to be HP 62. We're going to have another word, 155, that'll be minor. And then we're going to have our ASCII terminated string. ASCIIs, yeah. No, I want actually complete control over it, so I'm not going to write that. Zoltan. And then I want to have 7 zeros after it. If you can do that. That's not going to work, is it? I forgot how to do my records. How do you do those zeros within an ASCII record? I'll add some bytes. How many bytes do I need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is this going to work? I'm probably doing something wrong. I should have revised my assembly directives more clearly last night. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll have a look in a minute when we compile my code and see if it has entered memory correctly. So I'll just write a little bit of code here to access my record. Letter, R0, I'll get rid of these things. Zoltan stats, it's going to be an R0. So that's the address of my record. Someone help me in the comments and tell me the better way to do my ASCII 0 padded ASCII string. I'm drawing a blank on my memory of assembly directives right now. I might access some of my data. I'm going to do that by doing some offset loads. So I want to access my HP. I'll put that in R1, and that's going to be R0, offset 0. That one was easy. That'll get me HP. And I'll want to get my mana, which is going to be offset 4. And then I want to get maybe the first letter of my name. I'm going to just go do a letter B for that one. 0 offset 8. All right, hope this works. Oh, it worked. Lucky. Okay, so we got my memory address for my record, 2 followed by 7 zeros. I've loaded up my mana. I'll just go to natural. Loaded up my HP, which is 62 there. That's probably a bit small for everyone playing along at home. Get rid of my terminal, don't need that. I've loaded up my mana, which is 155. And I want to get the first letter of my name, which is the ASCII address 90. What's 90 in natural, in dec? It's a capital Z. I don't know if you can see that. It's on the right side of the screen. I'll put it over here just to prove I was right. 90 is a capital Z over there. 132 in octal, 90 in decimal. Okay. Now let's have a look at my record in memory. Memory view OX2000 1, 2, 3, 4. Now how many bytes in length was my record? I know that it starts with a word, so that's 4 bytes. 4. I know it's got another word, so we've got 8 bytes so far. 8. I'm going to run out of fingers in a minute. And then we've got a 16-byte string. So we've got 8 plus 16, which is 24. I'm just going to enter the length and just to take exactly that number. If I just give myself some more space here, we can probably see the Zoltan. There it is. So I've got my first 4 bytes. That's my HP. This is going to be my mana. Then I've got my string, Zoltan, and then I've got all my zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Looking good. So, Oh, thank goodness one of my tutors told me what to do. Where's my students? 4, 5, 6, 7, 8, 9, 10. Will that give me the same thing? I'll know because if I have it wrong, there'll be a 2300 after it. x2, 1, 2, 3, 1, 2, 3, 4. 24. Oh, it's worked, I think. Zoltan followed by, there's my Zoltan, followed by 10 zeros. What are my tutors doing watching the lectures? Don't you guys already know? I'll take any viewer who wants to be a viewer, whether they're a tutor or a student. Thanks for that, Nick. Now, what am I going to do now? I've got my Zoltan, but really, like, it's so far not very useful code, is it? Ooh, how do I know where the name ends in memory? How do I know where it ends in memory? I tell you why, because HP is defined to be exactly one word, 4 bytes. Mana is defined to be exactly one word, 4 bytes. And in my definition of the character array, name was going to be 16-byte ASCII string. So it's always 16 bytes. Always 16 bytes. So that means I know that the whole Zoltan data structure is 24 bytes long. Fixed length. Fixed length. Great question. We're going to talk a little bit more before we finish today about this idea of allocating memory. Allocating memory. Because it's a tricky topic, and we'll actually do a little bit of an experiment here. But I want to do a few more things with character stats first. The next thing I'm going to do is to make another character, because it's more interesting to deal with records when you have more than one of them. As arrays, sometimes you're just needing one, because you've got a whole bunch of different things all together. You don't need more than one array to have fun or for it to be a useful data structure. But for records, really, once you have multiple of them, things start to really open up. So let's do another character stat. Someone in the chat give me a name for a character, please. I'll just see where my lecture was going, because I've just possibly gone off piste here. Oh yeah, memory allocation. So I'm not off piste. I'm doing things in the order I want, which is to do a long demo here. Someone's giving me a character, Bobby. Bobby stats. Another character struct. Okay, and Bobby is going to have, probably more HP. But less mana. I mean, Zoltan was magical, so obviously had a lot of mana. Bobby, how many letters do I got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Bobby the Sneak. Maybe Bobby is like a stealth character. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we're going to need one 0 to pad that string. Again, Bobby the Sneak is a 24-byte struct. So now I've got 2 characters. Why is this cool? Well, suppose I want to quickly get the the HP of each of these characters. Well, the HP is boring. What about getting the mana of each of these characters? So I could make a function which is going to get the mana for me, taking in a parameter. So maybe the parameter is going to be whatever is on the stack. The first thing on the stack. Or let's just make it R0. That's probably easy. Going back on what I said, no stack right here. Param equals base address in R0. Returns mana in R0. That's my function. So I told you all you need is the base address, and I'll tell you why. Because once I've got the base address in R0, I can do a very simple operation to get that mana. Now, no matter what character struct I have recorded with R0, this instruction is going to retrieve the second word in that struct, which will be the mana record, and put it into R0. So maybe I'll do it like this. I'll say BL get mana, and then I'll mov mana, use R5 to store it. And then I'm going to do the same thing with Bobby's stats. So now I've got a program which is going to get the mana of Zoltan and Bobby, and we can do something with it, right? So maybe we want to have some kind of mana battle, and we'll just compare R5, R6, and if it's equal, we go to, or if it's less than or equal to, maybe we'll say BQ, not BQ, what do I want? Maybe greater than or less than. I want to have some kind of outcome of the battle. If it's less than, that means that Bobby wins, right? Otherwise, Zoltan wins. Maybe I've got this wrong here, and you'll tell me I'm completely wrong in a minute, but Bobby wins. Okay. I'm sure I've done something wrong. You'll tell me in a minute. We'll get my Zoltan stats address. That's still the same as it was before, 2 with 7 zeros. Then I get the mana for Zoltan. I'm putting that into R5, OX9B, 155, that's correct. I'll get my Bobby stats, which should be 2 7 zeros plus 24. That's 24. 2 followed by 5 zeros followed by 1 8. Get the mana for Bobby. Bobby doesn't have much mana at all, only 31. Put that into R6, compare R5 and R6, and Zoltan wins. Sorry, Bobby. In a mana battle, you're not going to win. So, you might start to see how these offset things are actually pretty useful, because they let you access all the fields with just the one piece of information, just your base address. You make a slightly more complicated function that accesses multiple bits of data. Maybe it's if you try to do a power mana move, it is going to, it's going to multiply your mana by your HP, and that's the power of your move. That'll be returned. And it will then remove some of your HP. So storing it back. Let's try this one. Power, mana, move. So it's going to calculate get your mana and get your HP. I better not use R1 because R0 is going to be the parameter. R2, R0, that's your HP. And it really doesn't make sense to have them in that order, does it? Almost had something was slightly confusing. Okay, so now we've got to calculate power, mana, move, power. R3, mul, R3, R1, R2. R3 is going to be defined to equal HP times mana. And then we've got to calculate new HP. So he's sacrificing some HP to do this move. So we do R1, maybe it's like 10% of, that's too complicated. We'll just subtract 5 from HP. How about that? Sub R5, R5, 5. What? Why R5? R1. And then we're going to store it back. Store new HP, and we return our move power in R0. Okay. Ooh, what if it saves this, instead of returning it as the move power, it saves it in your mana instead. So it's a power mana power up. I'm thinking on the fly here because it's fun. Isn't thinking fun? I'm going to store my new R3 in my offset mana. This is going to turn the tables in this battle. Store new mana. Alrighty. So, probably have to save some things on the stack here. I know I'm only using R1, 2, 3. Not R0. And R5 and R6 are safe so far. Of course, if I was doing more work with those call save registers, I would have to push and pop them. So I might just do that here, just in case. So now, here's the battle. Zoltan's going to start. We're just going to get Zoltan's mana. Bobby's going to do the mana power move. Then we're going to get Bobby's mana again. We've got to probably just a good idea to chuck that stuff in there. And then we're going to do our comparison of mana and see who wins. Let's see if this program works. As always, I'm pessimistic. Am I using the emulator? That's interesting, okay. Getting the mana from Zoltan, 155, VXLR. Storing that mana from Zoltan at R5, 155, cool. Okay, we're going to do Bobby's power mana move power up, pushing stuff on the stack, get Bobby's HP, get Bobby's mana, calculate Bobby's new mana power, which is 4,495, pretty impressive. Subtract 5 from Bobby's HP, so still still in the black there, still with positive HP. We're going to store our new HP into our Bobby record. We're going to store our new mana power into our Bobby record, pop off those registers if they were changed, and return. So now Bobby's got a new record. So we're going to get Bobby's mana this time. Just get Bobby's address again in case we lost it. You never know what's happening in a function, so you better make sure you keep track of your caller saved registers. We'll retrieve Bobby's mana, 4,495, BXLR. Great, now we've got a new kind of battle. Bobby versus Zoltan. We'll see who will win. Compare R5, R6, and we go to Bobby wins. So we did it. It only took us half an hour to create a very valid battle. So, a few things to point out. This is a lot like what you were doing with the Pokemon or a little generic animal game character lab in week 3. What have we got which is different? We have functions. We have a way of storing data in memory, which is really sensible. So can you see how now with these tools, you could make something much more interesting, a much more interesting program that's able to really save data in a sensible way in memory. By the way, if we now look in our memory, we should be able to see these updated Bobby and Zoltan representations. So I'll just go 1, 2, 3, 1, 2, 3, 4. I'm going to see them both at once. So 24 times 2 is 48. Get both of my, I just want one. Both of my representations. So here's Zoltan. That's Zoltan's HP, that's Zoltan's mana. There's Zoltan's name. Here's Bobby's HP, is 8C. Here's Bobby's mana, which is much bigger. 4,495. It's 11118F in hex. Of course, this is in Little Endian. 8F11. And then there's Bobby's name, Bobby the Sneak. He is a sneak. If Bobby can use a move like that, what a sneaky character they would be. Okay, what's next? We could have fun all day creating a kind of record-based game, but I'd like to try something else in a minute. We'll have a look at another topic. Composite data structures. Well, I think we've really got to the point of this in what we just showed you, because I showed you that you could have an array inside a record. We had an array of ASCII characters, ASCII bytes. I also showed you that you could have a record inside a record. Well, you could have a record inside a record, but with the same technique. Just have it there, and the offset from the base address of the parent record is the base address of the child record. You could have an array of records. We could have many characters in a huge array. That would be useful. I am moving up the array by 24 each time. All kinds of interesting ways of representing data in memory with assembly. One thing to remember, the question is, are these things object-oriented objects like you learned about in Comp 1110? No, they're not. They've got the variables or the fields, but they don't have the methods or the functions that are associated with an object-oriented object. For Java to do that, it has to have, as part of the objects, a table of locations for functions that are associated with that object's fields. So it's a more complicated arrangement for the way things must work in Java. Next, memory allocation. Memory. What does it mean to allocate memory for an array? What does this mean? Someone pop in the chat if you've got an idea about what this means to allocate memory to an array. Tell me now. I'll give you a second to think about it. Someone suggested memory allocation for an array must mean the fixed size of an array is its space allocation in memory. Yeah, that's true. So if we have an array of a fixed size, its allocation in memory must be a chunk of memory which is dedicated for that array. And I guess my question is, what does that mean? Here's our array, and we've decided to allocate it some space in memory. It's got maybe it's an array of 100 integers. So we're going to give it a base address. Whoops, any other clue? It also means we agree not to write over that bit of memory too. Yeah, that's good. So when I say this is an allocation for this array, for the array, I'm really saying two things. One is, it's not in use by anyone else, it's free. Not in use by anybody else, any other data. The second thing I'm saying is, we'll save it for you. Yeah, someone's saying it's to secure the data. Absolutely. So it's securing it in the sense that it's not going to be overwritten so far. It's not securing it in the sense that other people can't read it or other programs or anything. There's no kind of security part, but it's safe from being overwritten. So if we think of just imagine for a minute a concert hall with rows of seats. You know when you're booking seats for a concert online or booking seats for a movie, they'll show you some diagram of all the seats in the concert hall. And suppose you and two friends are going to go to a concert and you want 3 seats for the concert. So you go through this image, and some of the seats you can see they've been taken. Someone's sitting in them already. Can't sit in those seats. There are some free seats around, but there's not 3 together. And what we really need for our group of 3 friends is 3 seats altogether. I just came up with this analogy right then. I should make a slide about it. And you're searching for this location, and you finally find one, right? There's 3 seats all locked in. So you select those ones with the system for buying tickets, and you buy the tickets. And the system is now saying, these tickets are your allocation for your 3 friends. The person selling you the tickets, or the website, has given you some kind of assurance that the seats are free. When you go to the concert, you're not going to find someone sitting in those seats. Or if you do find them there, you can ask them to move. And secondly, they're going to save those seats for you. They're not going to sell them to someone else. So you definitely have 3 seats in the concert hall for you and your 2 friends to sit together. Happy times. So it's the same idea with allocating memory for an array. We must have some kind of system where we can make a guarantee that some memory is going to be free, the amount of memory you need is going to be free, and that we're going to save it for your array and not use it for something else later by accident. But how do we do that? We're going to make an assumption here, which is that we are asking for a fixed amount of memory. In fact, whenever you ask for memory in a memory allocation system, it's always a fixed amount. Don't want to blow your mind there, but like the concept of asking for a flexible amount of memory, it's like asking for a flexible number of tickets. Can I have a row of tickets together, but I'm not going to tell you how many people are coming? The website's going to be like, well, no, because then how can I sell any other tickets? You have to always ask for a fixed number of tickets, and then if your party changes size, you might have to change. All the tickets might have to change at once. So that's similar with dynamically sized data structures in programming. The amount of memory required is always fixed to start with, and then if it turns out you need more later, we'll have to do something else. The system has to figure it out and move the memory somewhere else. Okay, that's enough scribbling on that slide. Smalloc, the silly memory allocator, or a small memory allocator. So we're going to make a memory allocator which is very silly and very small, and just shows us this concept in practice of saving memory, saving my seat. Can we save the array's seat? So now, I've already got a bunch of stuff in my memory, but I'm going to add another thing at the end, and it has to be at the end. Smallic value. It's going to be a bit tricky to do this, but I'll add it up. How many bytes was this? 24 bytes. How many bytes was this? 24 bytes. How many bytes was this? 1, 2, 3, 4, 5, 6, 7, 8. So it's 48 plus 8. So far I used 56 bytes of space. So what I'm going to record here is a number, which is my first free area of memory after my statically declared data. So this is memory which is going to be allocated and filled in while the program is running. I'm not declaring it with .words. So this is the location of my first free bit of memory. 2000, it can't be 0000 because that will end up referring to Zoltan stats. That's not going to work. So it's going to have to be that plus 48. 56, I mean. What's 56 in hex? Get a calculator out. 56. Oh, it's not the wrong point of view. Programmer calculator. Thank you. In hex, OX38. So all of this one takes up OX18. This one takes up OX18. This one takes up OX8. And then we have OX38 as our leftover. Okay, so go back. We've got a slide here to start preparing this concept because it's a bit of a tricky one to remember. All of our memory so far has been very simple. We've declared it when our program is being compiled, so we know everything about its structure. But now we're changing, except for the stack, but we're now changing to kind of unknown territory. Things are going to be happening at runtime while our program's running. So we're going to describe the Smallic function. At minimum, the Smallic function must take as an input parameter the number of bytes which are required. So that could be, the analogy is the number of seats in the theater. And it's going to return a memory address pointing to the base address of that many bytes of free memory. We guarantee that this memory is going to be free, and we're also guaranteeing that we're not going to sell that memory again. We're not going to give it to anybody else. So the way we're going to do this, going back to a slide where I can draw, we've got our static memory so far, right at the bottom of memory, OX2000, 1, 2, 3, 4. We know we've got Zoltan, we know we've got Bobby, we know we've got our 2300 array, and we worked out that that was taking up a total of 56 bytes. So after that, we're going to have our area that the memory allocator is going to give you memory. Of course, right at the top of memory, we've got the stack coming down. They're very far away from each other right now. Far. So we're not in any immediate danger of overrunning each other, but it could happen. That's the stack coming downwards. So our static memory allocator is going to define start giving out this memory, starting after our data structures that are statically allocated. Start giving out this memory at runtime, starting with the first bit that's free. And I realize I've just made a mistake. It's going to start with that bit. This, by the way, this area of memory is often called the heap, which is not referring to any special data structure. It just refers to a bunch of memory with everything jumbled up and we don't know what's happening and it's runtime and it's up to the memory allocator to figure it out. So memory that is used during runtime of your program is often called the heap. So every time I run my allocator, it's going to take the first free address, deliver it to the person who ran BL Smallic, and then move my pointer of the first free address up. So the first free address starts pointing to there, and then if someone asks for 8 bytes, I'm going to give them the first free address and say you've got 8 bytes here, and then I'll move the first free address up by 8. If someone asks for 100 bytes, I give them the first free address, and then I move the first free address up by 100 bytes. Very simple. Now, I realize I've made a mistake already because this number is pointing to Smallic value. I'll keep my power mana move function, but I might actually just put it down in my other text area because I want to save it for later. And my get mana function. Get rid of those. Just put them down here. And I'm going to just gonna put a bunch of comments in there for now. So letter zero, just for argument's sake, I'll load in my first free value and just see what address that is. Oh, it's 0050. Did I make a mistake here? Oh well. Made some kind of mistake. 2, 3, 4. I'll just go with it. That's the address of this label. Oh, I'll set it up. Store. I'm going to add 4 to it. 04 and store it back. Oh, that's not going to work. Store in R1. R1 will be the first free address. Always better to do something programmatically than try to hack it out in your head sometimes. So this is the label Smallic value. Okay. So Smallic value now contains that 0x54, 0x2 followed by 5 zeros followed by 54. I'm just going to make this 0 for now. Need to update this at start of program. So first, free memory at start of program. That's right. So someone's reminded me that this is not an array of bytes, it's an array of words. So it was not in any way going to work. So that's 1, 2, 3, 4, 8 words. That's 24 bytes. That was, in fact, 3 times 24 bytes. Anyway, I've written my program now to solve my problem for me. So this memory location, Smallic value, now contains the first free memory after all of these statically allocated bits of memory, and which should be 0xx, 0x2, 000, 0054. So the value, the address of this word is 2000050, but we want the word after that, which is the first free memory. Okay, now I'll make my function. Smallic. So it's going to grab, Smallic's going to take one parameter, 0 is number of bytes requested. Returns base address of allocated memory in R0. Okay, so first things first, I've got my parameter. Now, we had stack frames before. A good thing to do is to just save your parameter because we might want to use it for something else. So I'm going to push R0 onto the stack. So then what do? I load up my current base address. I'll load it into R0, in fact. Smallic value, so load first free address into R0. So now in terms of the return value, we're done. We can just return this first free address. But we need to do our allocation bit of preserving those seats, saving the bytes in memory by moving our pointer in Smallic value. Oops, actually it's not that. That's the address of our first free address. Load address of first free address in R0. What am I thinking? Folks, I almost made a terrible mistake. R1. Wait a minute. Use R2 for that so we can just get it straight into R0. Why would I use R2? I'll use R1. Sometimes I just use weird registers for no reason. I'm not sure why. Load address of the first free address. Okay. R0 is first free address. So now we're done. We can just return that R0. But I need to get that update the first free address stored at Smallic value. So I'm going to get back my parameter, which was the number of bytes required. I'll put that in R2. And then I'm going to say add R2, R0. So R2 is now new Smallic value. And we're going to store that back in that stored global variable for our first free address. And that's all our function is going to do. So if I run Smallic now, this is setting up Smallic. Okay, we're going to allocate 100 bytes. Hope it works. We're setting up Smallic with its correct value, the first free address. Now I put 100 into R0, go into my Smallic function, push the 100 on the stack, load the first free address. Oh, that's the address of the first free address. Too many addresses here. I've loaded it in, 2 followed by 5 zeros followed by 5 4. Pop back my offset, which I need to change that address. This is my new first free address, and I store that back in Smallic value. And then we can BXLR back to my program. Okay, so let's just check out our memory to see what was going on. How many bytes of memory am I going to take? I had 24 times 3 was the static data, so that's 72. And I'll take a bit more than that. Maybe I'll just take 128 bytes. I'll put it over here. So first things first, there's our Zoltan data, there's our Bobby the Sneak data, then we've got our 2300, 6300 data, then we've finally got our record of the first free address, which should be OX200000B8, and as you can see it is, in little endian order, B8000020, 200000B8, in the human readable order. And the memory after that is just full of nothing, initialized to ones. So we haven't written anything there yet, but we can be assured that that memory all the way up to 200000B8 is free and can be used by our program for stuff. So that is our silly memory allocator. So where are we now? There's another, I've got it in a slide here, another version of the program, slightly different, slightly the same. Let's just have a little chat about real Malloc, real memory allocator. If you're writing programs in C, you will use a function called Malloc to give you some memory to do stuff with. So real operating systems provide some kind of function that will allow programs to dynamically grab some memory. And it sort of works like this. It's got some extra features. At a basic level, the extra features would be giving you some way to free memory or release it after you're done with it. So if you say you don't need these seats at the theater anymore, the system can sell it to someone else. It'll have some way of keeping track of memory allocations using metadata. In fact, what regular normal C Malloc will do is add a little struct at the start of the allocated memory saying whether it's free or not and how many bytes there are. So you can always go through your memory afterwards and find these structs, find the next one, and sort of start to add up the memory which is free to potentially sell it to someone else. And Malloc will also try to fail gracefully when it can't give you enough memory. In C, if you call Malloc and if you run out, don't have any more memory, it just returns a null pointer to nowhere to tell you that it's can't do it. So you have to do something else with your program. So I've got a few links in the reading part of this this lecture explaining how memory allocation works on different operating systems with different considerations, different platforms, different situations, old and new. It's a very deep topic. It's something that you would learn a lot more about if you were taking an operating systems course, but we can give you an overview in COMP2300 about how you might be able to allocate memory dynamically while a program is running. I'm sort of wrapping up in a minute. I've got a few more slides, but they're basically showing worked examples of what I just did with the Zoltan and Bobby the Sneak character examples. So if you've got any questions right now, chuck them in the chat. I'll just have a look and see what's on these slides and see if I haven't missed anything. Data structures and argument passing. Oh yeah, this was, as we were doing, we had argument passing through registers in our examples with Zoltan and Bobby the Sneak. We had this, here's a Zoltan the Magnificent data structure. And this function is passing the character data in just as registers into a function. So it's not actually, the function itself is not doing the reading, which is not what we wanted to do. We wanted the function to do the reading rather than the function just looking at the values in the stack or in registers. So this is what we were doing. We would load into R0 the address of Zadok the Magnificent, and then our function itself loads in the HP and does some calculations to work out if Zoltan is still alive or not. Yeah, here's your further reading. I haven't seen any questions. I guess everyone is busy studying for all of their mid-semester exams. So I think I'll wrap it up now. Next week we have some incredibly important course content coming up. So if are in any doubt about attending your lab next week, do it. It's very important that you go to your week 8 lab. It's very important that you watch the week 8 lectures. I'll hopefully find a way to lecture at a more convenient time, maybe on Monday night, so that it's more easily available to everyone during the week. Because next week we start to use the buttons on the microbit, start to get inputs and learn about how that works with this concept called interrupts. It's one of the most important weeks of content in the course. And you thought all the other stuff was important. This stuff is really important to enable you to do the assignments that are coming up. So get through the exams this week, get through the exam for COMP2300, of course, and I will join you next week for that really super important and detailed concept. Yeah, there's a few people saying Monday night much better. I think I would like to do that too. So I'll just have to work out how it's going to work for me, but doing a live stream in the evening when more people can view it, I think would be fun. Okay, so I'm going to stop my recording in a minute and say goodbye to you. Have a great day. Good luck with all your exams this week, and I'll catch you next week.